Okay, so sampling and estimation are key topics that will spill over hypothesis testing. We need to understand key thoughts. Number one, why do we sample? Why is sampling important? So this why question answers a few highlights that I can talk about. Number one, sampling is important because when you're using a sample as opposed to the entire population, you save money. So we are constrained financially because of financial constraint. The other reason why we sample is because of time. Time constraints. The other reason why we sample is because of accuracy. A sample may prove to be more accurate than the whole entire population. Sometimes we sample because of sufficiency of approximation. It may be sufficient to use a sample to represent the entire population. So it is vital to use a sample as opposed to the entire population. Also, sometimes the universe size will be big. No matter how much money and time you may have, you may not really categorically have enough to ascertain how many people have contracted COVID this whole world. So we'll look at sampling and estimation. Specifically, we'll look at key themes like confidence intervals and how to come up with the sample size calculations. All right, so the concepts here we're going to fortify on will be understanding the reasoning of statistical estimation, how to calculate what are called the margin of error, and the concepts of confidence interval, what a confidence level is, how to calculate the confidence intervals for a population mean, and how confidence intervals behave. This is what we're going to look at. So the objectives of this chapter will be: number one, to define statistical inference; number two, to describe the reasoning of statistical estimation; to describe the parts of confidence interval and interpret a confidence interval conclusively, and also to construct and interpret a confidence interval for a mean, and also to describe how confidence intervals behave. So, statistical inference. The purpose of collecting data on a sample is not simply to have data on that sample. Researchers usually take a sample in order to infer from that data some conclusions about the wider population represented by the sample. So a statistical inference in this regard simply provides methods for drawing conclusions about a population from a sample data. So the entire population, which is a census, the subset is called a sample. So when you collect data from a sample, it is a representation of the entire population. So we're able to make an inference, a conclusion about this entire population. Now, it is very vital for you to understand this topic because when you'll be doing your data analysis in your final year doing your dissertation, it is out of the population that you're going to calculate your sample size that you use to give an inference about the population. So every researcher must understand. So we're going to cover how to estimate the mean of a variable for the entire population. So when we go down here, There are a few conditions that you need for an inference to be made about a mean. Number one, that the sample must be randomly selected. Number two, that the variable of interest must have a normal distribution. Number three, that the population mean must be unknown, but the standard deviation must be known. Number four, so these three conditions are very important. Of course, these conditions are very difficult to meet in a real situation, especially when you're dealing with social science researchers. But there are other procedures that need to be followed when these conditions are not met. And these conditions will be looked at length later on. So we're going to look at the formulas for estimation. We have the confidence interval formula, which is given by C. Confidence interval is equal to the mean x bar plus or minus the mu, the mean plus minus z. This is a two-tailed test, standard deviation over the square root of n. This is mainly for samples greater than 30. And also the sample size formula is given by the formula z squared, the variance over the level of precision, which is E. So having gotten this formula, we also need to understand the key levels of confidence. So we have 99%, we have 98%, we have 95%, and we have 90%. The significance level is a difference from 100. So 99% is the same as 1%. 98% is the same as what? 2%. 95% is the same as 5%. And finally, 90% is the same as what? 10%. So this is called the level of significance. This is the confidence level. Then when we divide our level of significance by 100, this is called our alpha. So this is 0.01. This is 0.02. This is 0.05. And this is 0.10. Okay. Then in a later session, I'll discuss with you how these Z figures are calculated. But for now, these are standard ones. So 99% is 2.575. This is 2.33. This is 1.96. And this is 1.645. Right, so the confidence levels for a normal distribution. So these are called significance levels. So if you have 5%, as a significance level, and it's a two-tailed test. So this is 2.5 here. We divide the 5% by 2 on this left and the right tail, and this is 2.5. This is a level of significance. And what remains here is your 95%, which is your level confidence level. So if you have a confidence level of 99%, this means your Z is 2.575. If your confidence level is 98%, meaning significance level is 2%, your alpha is 0.02. Your Z is 2.33. Now, I'll take you quickly to a few questions based on the formulas. Find the missing, find the sample size. If your alpha is 0.01, your error is within plus or minus. So error comes in the word within plus or minus 4, and your variance or standard deviation is 25. So find your n. So n formula here is given by z squared variance over the error squared. Our z is 1 point. So from this is the same as 99%. So 99%, if you're able to remember what was the z for 99%, from the table, our 99% is 2.58. Some books will give 2.58, which is the same as 2.575. And our standard deviation here is 25. And our error is 4. So the sample size you are given here will be calculated from the computation that we may have here. So what are we getting as a sample size? What are we getting as a sample size? So when we go to our calculator, so we have 2.757 squared times 25 squared divided by 4 squared. Final answer will be 296.91. 296.91. 296.91. So meaning the sample size that is required is 296 for us to be 99% confident. Now notice here that this was our what? Our standard deviation. If we're given our variance as 25 instead, what we would actually have here is 2.575 squared times the 25. But we're not going to square this 25 because it's already given as a variance. Alternatively, you can write 5 squared there because the square root of the variance is a standard deviation. So that is where you can get your final answer there. So you can still use the calculator to calculate. So 2.757, 2.575 squared times 25 divided by 4 squared, which is 16. You get 10.36. 10.36. So these are the small mistakes that most students make once they fail to understand. So this is simply when you're dealing with variance or when you're dealing with the standard deviation. So whenever we're dealing with a proportion, our formula is z squared pq over the level of precision, which is the error. The relationship between p and q is such that when p is 80%, q is a remainder from 100, which is 20%. So the relationship between p and q is that of the confidence level and the significance level. So suppose we're given the level of significance as 2%, and our proportion of p is given as 30%, and the level of precision or the error is given as plus or minus 4%. Now get me right here. Our song still needs to sound. Remember, 99% one is the same as 1%, which is 2.575. 98% is the same as 2%, which is 2.33. 95% is the same as 5%, which is 1.96, and 90% is the same as 10%, which is 1.645. So you need to have these table at your fingertips. You need to have the table at your fingertips. All right, so here we're going to now substitute where there is z. We're going to put in 2%. Remember, this is our song. 99, same as 1%, same as 0.01, same as 2.575. 98%, same as 2%. If you're converting it to significance level, so same as 0.02, which is 2.33. And 5%, same as 5%, which is 0.05, which is 1.96. 90%, which is same as 10%, which is 0.10, which is 1.645. This is 5 here, sorry. All right, so in this case, since the 2% is the same as the 98%, the Z figure here is 2.33. 2.33 times our P, which is 30%, which is 0.3, and our Q, which is 70%, which is 0.7, and our level of precision, our error is in percentage. So we also write 0.04 here, the power 2. So that is how we substitute our figures there. I may not really be interested in the answer, but how to substitute the figures there. If we're given our alpha as 0.10 and our P as 40% and our error as 10%. So the same application here, Our n here is z squared. Our z here, 10% is 1.645. 1.645 squared times our p is 0.4. Our q is 0.6. Our error 10%, which is 0.10 to the power 2. You can get your answer there. So this is how sampling is done with the formulas that we have just looked at. I'll take you through how exam questions look like. At this point, I'll ask if there are any questions. Are there any questions at this point before I move? So let me give you an example that can be applicable to what we've just discussed here. So whenever we're dealing with sample size, the examiner will be very quick to mention what sample size is needed. Okay. So I'll take you to an example. Let's look at this example. You want to estimate the average hourly output of a machine to be within 1.5 plus minus with 90% confidence. Based on historical data, you have reason to believe that the standard deviation is 6.2. How large a sample do we need? So to start with, what have we been given? We've been given our error, which is plus minus 1.5. Our standard deviation, 6.2. Our confidence level is 90%, which means our Z at 90% is 1.645. So we need to look for our sample size, N. So if our Z is 1.645, we use this formula, N is equal to Z squared times, so using this information, let me simplify it from what we've just discussed. This is how the exam setting will look like. So you just simply need to simplify the data the way I showed you. So this data has been given here. What can we simplify from there? Number one, our error is 1.5. Our Z, since we have 90%, is 1.645. What else do we have? 1.645 is coming from where? It's coming from this 90%. Then we've been given our standard deviation, which is 6.2. So remember, N is equal to what? Z variance over error. So if you substitute all this, we have 1.645 here. Which is supposed to be squared. And our standard deviation is 6.2. over 1.5 squared. So if you calculate this, you will get your value as 47, 46.22 as 47. This is our actual value of n. So this is how we do the sample size formulation. Then when you go to estimation, we're looking at confidence interval. For confidence interval, we have mu plus minus z. It's a two-tailed always. Standard deviation over square root of n. Remember, we always use z if the sample size is greater than 30. So if you're given a mean of 10, an alpha of 0.05, 5% is usually the standard. If you're not given any, we'll pick on 5% as a standard. Our standard deviation is 12, and our sample size is 36. So we can use a z because sample here is more than 30. So using this formula, just substituting here, we put a 10. Where there's z, we're going to put a 1.96. And the standard deviation, 12, and square root n, which is 36. So here we're going to have 10 plus or minus 1.96. And then square root of 36 is 6 into 12. We're going to have a 2. So when we're going to multiply, we're going to have 3.92. This is called our margin of error. So we're going to subtract to get the lower boundary or the lower class limit, 10 minus 3.92 and 10 plus 3.92. So 10 minus 3.92 gives us 6.08. So here you're going to put 6.08. Then the upper class limit, we're going to have 13.92. So this is how our confidence interval is calculated. All right. So we were given a mu of 10, a standard deviation of 12, our alpha at 0.05, and our n as 36. So using this formula here, we're simply substituting. Our mean is 10, our z is 1.96, and our standard deviation is 12 over 36. So when you compute this, we get what we call standard error, or margin of error. When we subtract 10 minus 3.92, we get this. 10 plus 3.92, we get this. And we comment in terms of the confidence level to say we are 95% confident that the true mean will lie between 6.08 and 13.92. Suppose we're given mu is equal to 100, n is equal to 49, standard deviation is equal to 21, and level of significance is equal to 2%. So we still use the same formula. confidence interval is equal to what? Mu plus minus z standard deviation over the square root of what? N. All right. So our mu here is 100. Our z is 2.33. Our standard deviation is 21. And our n is square root of what? 49. So we first need to calculate the margin of error. So square root of 49 is 7. 7 into 21 is 3. So we multiply the 3 to the 2.33. What do we get when we multiply the 3 to the 2.33? We get 6.99. So to get the lower class boundary, we first subtract 100 minus 6.99. 100 minus 6.99, what we get? 100 minus 6.99, that is 93.01. 93.01. So we have 93.01. In the upper class, we have 106.99. So we comment in terms of the confidence level to say we are 98% confident that the true mean will lie between 93.01 and 106.99. So this is how we find the confidence interval for a sample mean. We could as well find the confidence interval for a proportion, which is given by P plus minus Z. Here we have PQ over our N, everything under a square root. Okay, so suppose we're given a sample proportion of 30%, and we're given our confidence level as 99%, and we're given a sample size as 50. Let's find the confidence interval for this proportion. Okay, let me say our sample size is 100. So using this formula on top, what is our proportion? Where there's P, we put 0.3, because that is 30%. And our Z coming from the confidence level will be 2.575. Then our P, 30%. The remainder is Q, 70%. And our N is 100. P and Q must always add up to what? 1 or 100. Sample size is N. So 0.3 here plus or minus 2.575. And here 0.3 times 0.7 divided by 100, then is square root. 0.3 times 0.7 divided by 100, then we square root that. So 0.01, then what do we get when we square root that answer? 0.002 0.0021 on your calculator. How do you what are you getting when you square root? Square root 0.0021. Confirm what you're getting. 0.045. 0.05. Okay. So when you multiply this 0.05, multiplied by 2.575, final answer is 0.118. 0.118. So 0.3 plus or minus 0.118. And at this point, it's easier to convert them into decimal or percentage. Sorry, this is 30% plus minus 11.8%. So when you subtract 30 minus 11.8%, what are you getting? 30 minus 11.8, you get 18.2. So here we have 18.2%. And the upper limit will be 41.8%. So our comment will be, we are in fact 99% confident that our true proportion will lie between 18.2% and 41.8%. So this is how we do estimation with regards to the proportions. This is how we do estimation with regards to proportions. Unless there are any questions at this point, if I take you to an exam question. Okay, so we'll look at one example of how to calculate confidence interval for a mean from what we have just looked at now. We're going to look at computing the confidence interval for a mean from what we've just discussed. So now we're going to look at a practical example of how the exam setting comes in for confidence intervals. So we have this question here, which came in one of the exam papers. So we are being asked to calculate the confidence interval. Now, I'll paste the question here so that we're able to work on it together. All right. So here we're told that a chain store is interested in the expenditures of sporting by high school pupils during a winter season. A random sample of 58 high school pupils yielded a mean winter expenditure of 168 rands. Assuming the population standard deviation is 37, find the 95% confidence interval of the true mean. So in this case here, what are we given? We know that the formula for confidence interval is given by mu plus minus z alpha over square root of n. So what are we given here? Our n is what? How many sample pupils? 58. Our average, our mean is what? 168.15. and our Z is going to be what? 1.96, coming from our level of confidence. And also finally, our standard deviation is 7.6. The data that has been given, we now substitute. Here we're going to have 168.15 plus minus Z of 1.96, and the standard deviation was 37.6, and our N was 58, which is above, way above 30. So we're going to use our Z. So here I've taught you how to find the values of the margin of error, and we subtract to get the lower bound, which is X, and add to get the upper bound, which is Y. So this is how we calculate. So we're just looking at sample questions from the exam. Here we're given an estimate mean of fuel consumption per 100 kilometers of a car is required. A sample for 7 drivers. Each drive the car under a variety of conditions for 100 kilometers. So the 100 is simply a condition within which the drivers are subjected to. Not that we're going to use it in the computations. The fuel consumption is measured and the sample mean turns out to be 6.73. So this is our mu. Then we also given our standard deviation as 1.7 per 100 kilometers. We are asked to find 95% confidence interval as well as a 99% confidence interval. The only difference we're going to have with these two is that our Z here will be 1.96 and our Z here will be 2.575. So this is how this has to be done. So I'm going to give you this as homework. Please follow through this video. Remember to follow up all other lectures on the YouTube channel, or directly contact me for the videos on the number showing on the screen. So I'll always send you homework just to check through what you have learned. For now, it's bye-bye until we meet next time.